Hello, everyone. Welcome to this webinar dedicated to nacelle-mounted lidars and power performance testing. My name is Elvira Liberdieva. I am part of our market and offering management team for wind lidars. And I'm joining you today from our Saclay office in France. And well, thank you for joining. And today we'll be sharing our screens. So I will go ahead and share my presentation. Just give me one moment. Okay, so today's webinar is dedicated to nacelle-mounted lidar and the changing power performance testing practices with the adoption of the new IEC 50-3 standard. I will kick off this webinar by giving an overview of the latest WindCube Nacelle enhancements in line with latest industry trends and practices. We will then have Reader with DNV, who will provide an overview of the new IEC standard and present results of the WindCube Nacelle classification. And then we will have Dale with GE, who will talk about 2G campaigns in North America, where nacelle-mounted lidar measurements were compared to the IEC MetMust. So today we have two guest speakers, Risa Dexter, who is the global practice lead for remote sensing at DNV and is a remote sensing expert. Since joining DNV in 2010, Risa has ensured the technical rigor of remote sensing measurement campaigns for onshore and offshore pre-construction energy assessments and power performance testing. Between 2019 and 2021, Risa was an advisory board member for IEA Task 32 on the application of LiDAR in the wind industry. And we also have today Dale Apgar with GE. After work in GE's coal gasification and asset condition monitoring businesses, Dale moved into onshore wind, focusing first on wind turbine blade design, then wind turbine validation and system performance. In this role, he helps set up and evaluate customer performance tests, prototype validation, and incorporating new alternative techniques in turbine performance evaluation. Before we go into our presentations, let me quickly cover a few housekeeping tips. So we'll have a Q&A session at the end of this webinar, and I encourage you to write your questions in the Q&A icon at the bottom of your screen, and we will try to answer as many questions as possible during this live session. And if we don't get back to all of the questions, we will make sure to follow up on you separately after this webinar. We also posted several resources in the resource section of this platform, where you can access the bio information of today's speakers and some additional information dedicated to today's webinar. And if you have any technical issues, you can click on the help icon at the bottom of the page to find answers to some of the common technical issues. And as usual, this webinar is recorded, and we will be sharing a link to this recording in a few days. All right. Before going into the, let's say, main part of this webinar, I would like to make a small recap of the last nacelle-mounted dedicated webinar, where we covered some of the market trends which positively impact LiDAR market growth. we see that wind energy additions are growing both onshore and offshore across different markets, both established and emerging markets. We also see continuous growth of turbines' power capacity, hub heights, and rotor diameters. And these factors make LiDAR technology more and more suitable for different types of wind measurement applications. In parallel, we also see a positive trend in nacelle-mounted LiDAR market penetration. So PPT practices more and more involve nacelle-mounted LiDAR technologies, both in established markets such as, for example, Europe, but also in Asia, Latin America, and other regions. And the nacelle-mounted LiDARs are already recognized as the standard practice for power performance testing offshore, and we see increasing penetration into onshore markets today. We also covered during the last webinar the nacelle-mounted LiDAR product development at Leosphere, demonstrating how our product adapts to the market needs and industry best practices. And today, with our WindCube Nacelle LiDAR and its flexible measurement range, we can easily meet our customers' needs and expectations, both for onshore and onshore applications. The industry has also gained experience with nacelle-mounted LiDAR through various joint industry projects that defined procedures and best practices on the use of nacelle-mounted LiDAR for power curve verification, such as, for example, EUDP and UNIT projects. And these kind of campaigns and continuous adoption of nacelle-mounted LiDAR in commercial projects have paved the way for this new IEC 50-3 standard. And at Leosphere, we have also worked with many industry players and opinion leaders to demonstrate the suitability of nacelle LiDAR technology for power curve measurements. And as you may know, nacelle-mounted LiDAR has been already included in many offshore turbine supply agreements, and we expect similar trend for onshore applications as well. So actually today the question that we want to answer is what has changed since the last webinar. And one of the major milestones for the industry today is the release of this new IEC standard dedicated to nacelle-mounted LiDAR for power performance testing measurements. The scope of this new standard is applicable for any nacelle-mounted LiDAR, and it describes how to obtain good quality measurements using nacelle LiDAR for power performance testing campaigns onshore and offshore. The standard also provides details on LiDAR calibration procedures, the framework for uncertainty estimation, and the guidelines for measurement campaigns. And in line with this new standard, DNV has performed the classification of WindCube Nacelle, and Risa will talk about the results of this classification in a few moments. Being the first LiDAR manufacturer to obtain this classification for our nacelle-mounted LiDAR, we can certainly say that it will pave further the way for increased usage of nacelle-mounted LiDAR technology for power curve measurements. In addition to this IEC classification that we just obtained, we also introduced a set of new product enhancements to make sure that our nacelle LiDAR meets the most recent industry needs and practices. One of these enhancements is the fact that WindCube Nacelle is now compatible with our web-based fleet monitoring software, which facilitates data access and Lidar fleet management. Today, you can access both WindCube vertical profilers and nacelle-mounted lidars through one dedicated platform. And along with this software update, we have also introduced Vizela pressure, temperature, and humidity sensor to obtain weather insights for air density corrected power performance testing campaign. And these data sets will be directly included in the Lidar data file. Along with this enhancement, we also introduced the rotor equivalent wind speed calculations to the Lidar data files. It comes in addition to the already existing hub height wind speed measurements, which in most cases is used for power performance testing. But we also today provide this alternative value in order to better understand the behavior of turbines with large rotors. And also in the resource section of this platform, you can access our recent scientific paper explaining in more details how we measure the rotor equivalent wind speed with WindCube Nacelle. And finally, we have also introduced several alternative mounting options in addition to the traditional tripod. Here, with these new mounting options, we would like to provide additional flexibility and facilitate Lidar installation on a variety of wind turbine models. And I also have a small video that I would like to show you on how our WindCube Insights Fleet software changed now that we included the WindCube Nacelle in the software. So you can see that we can have different, so we can have WindCube and WindCube Offshore here. And if we go into WindCube Nacelle measurements, there is this kind of dashboard where you can have access to wind speed measurements per each line of sight, and also 10-minute average wind speed and wind direction data. And then here in the wind data tab, we have daily graphs with additional data. For example, data availability per different range gate, and you have additional information when you go into the graph itself. And then the same information for wind speed, again for defined range gates, and additional information on the graphs as well. And the same goes to wind direction. You can see that there is per hour data in this case on the graph. And if we go back, we can also download this data directly from the software. And then in the configuration section, this is where you can add additional information on your campaign, provide information on the Lidar and the hub height of your turbines, but also define the range gates at which you want to do the measurement. In the diagnostic steps, this is where you can get additional Lidar status information. And if you click on a specific icon, you can have more information available. And then in the users tab, this is where you can add additional people who can access the Lidar data. And in the support section, this is where you can contact our technical support team in case you have any issues or questions. So this will be actually the end of my presentation, and I will now stop sharing and turn it over to Lisa Dexter from DNV, who will present the results of WindCube Nacelle classification.
Thank you, Elvira. My name is Lisa Dexter from DNV, as Elvira mentioned, and I sit in the North American office in the measurements team. And I'll just be sharing my screen to start. And I will present today the results completed by my colleagues Mark Andreas, Bastian Smit, and Jen Reitz. I'll begin with just going over some basic concepts of the classification per 50-3, and then present the results of the sensitivity and evidence-based studies. Before I do that, let's talk about some definitions that will be used throughout this project, this presentation. The first is LOS, which stands for the line of sight, and it is the magnitude of the wind velocity in the line of sight direction originating from the laser source along the axis of the transmitted laser beam. Intermediate values will be referred to throughout the presentation as well. And this refers to what the LiDAR is measuring. And these are the inputs to the wind field reconstruction model or algorithm, which processes these intermediate values into the final quantities that we use, such as wind speed and direction. So wind field reconstruction is the WRF, which is that process from intermediate values to those field quantities. And these are evaluated in the classification in terms of the environmental variables, those things that may influence the LiDAR measurements, such as shear turbulence intensity. So why do we classify LiDARs? Well, calibration of a single LiDAR device is done under a particular set of conditions. And these conditions during the calibration may differ from what you use on site for your power performance test, for example. And this introduces additional uncertainty. So the classification is a way to address these additional measurement uncertainties. I just wanted to take a step back and note that unlike a cup anemometer and a ground-based LiDAR where we get a class number, 50-3 does this a little bit differently and works between the calibration site-specific measurements and the classification results to provide an uncertainty. And this is done in a two-step approach. So the first is a sensitivity analysis of the intermediate values, such as the line of sight. And the second is an evidence-based approach, where we look to make sure that those significant environmental variables do not influence the wind field reconstruction model. To begin with, the sensitivity results. The WindCube Nacelle has 4 line of sight beams. Beams 2 and 3 were simultaneously measured from February to May last year, and line of sight measurements 0 and 1 were measured from May to October. The nacelle LiDAR was mounted on a 30-meter platform, as shown in the diagram to the left and the photograph of the site to the right. The line of sight beams are then pulsed towards the met mast to the north and south to compare those line of sight measurements with the anemometry. We then looked at a range of environmental variables as displayed on the x-axis here, and compared them to and then looked at the sensitivity of the LiDAR measurements. And this is done by comparing the mean deviation between the LiDAR and cup line of sight measurements, and we multiplied by the range which is the range of the environmental variable that was quantified as significant, divided by the square root 6. In this case, there were four environmental variables identified as significant. These were temperature gradient, air temperature, air density, and the wind shear exponent. After a decorrelation process, only air density and wind shear were deemed to be significant. In other words, air density and wind shear were independent variables, and temperature is highly correlated to air density and is therefore dependent. The temperature gradient was highly correlated with wind shear and was also deemed dependent, meaning that if we included temperature and the temperature gradient, we'd be double counting. So in this case, we have air density and wind shear as our sensitive environmental variables that the WindCube is sensitive to. From this, we get the slope of that relationship, and the maximum range from the classification. So how do we use this information? We assess the difference in the environmental conditions between the calibration and the specific measurements that you're doing on site, such as your power performance test. And then we get the uncertainty by taking the sum in quadrature of the products of the range of the environmental variables and the slopes. So I have two examples here. The first example is if I've calibrated my individual unit, but on site, I didn't have a measurement of air density and wind shear. In this case, I would simply take the maximum range as provided in the previous slide and multiply by the slope from the classification divided by square root 6, and then take the sums of squares of that to get the sensitivity and certainty. In the second example, I have measured air density and wind shear at my measurement location. And therefore, I take the difference between the calibration and the specific measurement campaign environmental variables and take the sums of squares of the slope and range of those to get my line of sight sensitivity and certainties. Moving on to the evidence-based study. So the objective of the evidence-based study is to make sure that the wind field reconstruction model is not sensitive to any environmental variables. That is, that when we take those intermediate variables and get a final wind speed, that wind flow reconstruction isn't impacted by those environmental variables. And in this case, the operational uncertainty of the lidar would be 0. So there's two parts to this. The first is that we take two tests where we put the lidar on top of a nacelle and face it towards a mast. The database requirements here are that we have 600 10-minute data points. 150 of these must be over 8 meters per second, and the other half below 8 meters per second. In order to pass this test, the bin-wise deviations must be within the reference uncertainty, in this case, a cup anemometer. So we did the first verification against a 120-meter turbine with a 167-meter rotor diameter, and we measured this 380 meters away from the turbine. And as we can see, we have fulfilled the database requirements as provided in the table in the bottom left. And to the right, we have the deviation between the lidar and cup measurements in red, which are the red dots. And then the blue dots are the reference or cup anemometer calibration uncertainty range. And as we can see, between 4 and 16 meters per second, that the deviation falls between the cup uncertainty range and therefore meets that requirement. At our second site, we had a turbine hub height of 89 meters, a rotor diameter of 127 meters, and a measurement range of 280 meters. Again, the database criteria were achieved and the mean deviation fell within the calibration range of the cup anemometers between 4 and 16 meters per second as required. The second part is an off nacelle test. So if you pay attention to the diagram on the upper right-hand side, we put the LiDAR on the 30-meter platform, and we pointed this towards a mast MM100 at 150 meters from the tower. In this case, the line of sight beams were pointed at 30 meters and 50 meters, 7 meters, and extrapolated to 44 meters. Here we did 4 tests. We had 3 separate units that were tested simultaneously between August and November, and then one of those units was tested again from June to August. In order to meet the requirements of the standard, a single parameter regression slope must be within 2%, and the coefficient of determination must be greater than 0.97. Here we have the results of these. So at the top, we have the concurrent period of the 3 LiDARs, and then to the right, we have the same device at the 2 different periods. And you can see that the correlations are well within the IEC requirements, and the databases were also fulfilled. So in summary, the WindCube Nacelle has been classified according to 50-3. Air density and wind shear were considered independent and significant environmental variables. All others were either insignificant or dependent on those 2 variables. We did evidence-based tests on 2 nacelle on-nacelle tests, which mainly fulfilled the accuracy criteria of 50-3, and 3 off tests, which fulfilled the accuracy criteria of 50-3. So what does that mean? It means that what that means is that the WFR model is not sensitive to any environmental variables. I'd like to now pass it to Dale Apgar at GE.
Thank you, Risa. Hi, everyone. My name is Dale Apgar. I'm an engineer with the Systems Performance team for GE Renewable Energy, and what I'll be walking everyone through today are results from our Nacelle LiDAR field validation campaign that we conducted last year. A quick note of acknowledgements along the bottom there. We are definitely beneficiaries of help from numerous people, and that's a short list of the contributors that helped with this effort. So last year we had an opportunity to install 2 of the Leosphere WindCube nacelle mounted LiDARs, and our objectives for these field validation campaigns were to deploy both of them onto GE wind turbines to examine the device accuracy, and in particular, how it relates to our power performance variables. So our method to do this was to compare the nacelle mounted LiDAR measurements against what we consider to be the industry benchmark, which is an IEC compliant met mast, and it's cup anemometry. So the focus today is really on the nacelle mounted LiDAR wind speed measurement and its derivatives, which are the shear exponent and turbulence intensity. And real quickly, what I'll walk everyone through here is, with the agenda, is to cover our strategy, how we set up these campaigns, and then walk through the results, which include scatter and bin power curves, the differences we saw in wind speed, turbulence intensity, and shear exponent. I'll wrap it up with some conclusions in our next steps. And that is an actual photo from, on the right there, of one of our deployments on one of our sites. So our strategy, there's many ways to go through one of these campaigns, and the temptation would be to go right into a full IEC compliant measurement campaign. But what we wanted to do first was to refine our focus on the essential variables. Namely, it's the wind speed, how that wind speed influences performance, and also the shear exponent and turbulence intensity. So we did that by centering our measurement sector from the turbine to the met, and centered it on the met mast. and we used for a directional filter the calibrated Met wind vane to filter the direction of the campaigns. I draw your attention to the two plots on the right. Those are schematics of those measurement sectors. So the blue pie slices that you see are perfectly valid IEC sectors, and they are large, and they can be used for a campaign. But what we wanted to do instead was, at least on a first pass, is to restrict those sectors so they're centered on the Met mast, but restrict them in size so we have maximum overlap between the nacelle-mounted LiDAR and the Met instrumentation. So yeah, so sites 1 and 2 along the top there, you can see that the blue is the larger IEC sector, but we're going to focus on that darker gray. It's tighter. It's about plus or minus 13 to 15 degrees centered on the Met. A quick note, there was no IEC calibration per the standard of either of these nacelle-mounted LiDARs in the test. The other schematics that I'm showing on the bottom right there is a visual of how the measurement areas differ. So the round circles indicate the turbine rotor diameters, and the dots in the center represent if the measurement is centered directly on the Met mast. You see the two dots that in the center of the rotor that would represent the Met mast anemometers, as well as the blue squares that represent where the nacelle-mounted LiDAR will be measuring. So if there are differences in the result, we can keep the measurement points and the measurement areas in mind if we do see some differences. So real quickly, we were, even with the smaller data sectors, we were able to capture rather large data sets, giving us statistically significant results. And just as a quick overview, what I'm not presenting here, but we're currently and actively considering is using the nacelle-mounted LiDAR wind direction, as well as the full IEC sector. So those blue sectors, what we're considering, just not presenting here. What we're also looking at is the alternative density corrections. When you get rid of the Met mast, you still need to correct for air density, and we're actively looking, as well as the net uncertainty that we're seeing from these devices. For bookkeeping, just a high-level filtering summary. The data that I'm showing is filtered for normal turbine operation, measurement sector, filtered using the calibrated Met mast wind vanes, data quality, following the IEC standard protocol. Icing points with a 30-minute buffer are removed, and the nacelle-mounted LiDAR data quality was addressed as specified from the manufacturer. Getting to the results here, here are two slides showing the scatter power curves for both Site 1 and Site 2. This slide is boring. If this slide seems boring, it's because it should. We wanted to take a look at the scatter power curves using both wind speed measurement devices, and what stands out is the fact that there are no major outliers between the two wind speed measurement devices. So that's good. The other thing that stood out in looking at the comparison of the scatter power curves is the fact that the precision, or the amount of scatter that we're seeing, is very similar between the devices. The expectation is that with a nacelle-mounted LiDAR, you'd have higher precision or less scatter because it's constantly looking at the wind in front of the wind turbine. But that's not really the case that we're seeing here. But we attribute that to the fact that we have such a narrow measurement sector that's centered on the Met mast. Next thing that we wanted to look at was looking closer at the wind speed delta between the devices that are measuring wind speed. So it's typical in comparing wind speed measurements between devices to look at regression. But in this case, what we're really interested in is looking at the wind speed deltas between the instruments. So what we'd consider a entitlement is the delta between a control and primary anemometers that are both resting on the Met mast. That's the chart on the left there. So it's a really tight correlation with less wind speed delta between those two measurements, but that's expected. What we also expected was there to be some scatter as measured in the wind speeds between the nacelle-mounted LiDAR and the two anemometers, which are the two plots that you see on the right. So that expected scatter is, again, related to that schematic that I showed earlier, where the nacelle-mounted LiDAR is measuring things over a duration of an area and in different points, as opposed to the single points of a Met mast anemometer. So we did see the expected scatter. But what's also superimposed here is how that scatter and that difference between the wind speed measurements manifest themselves in a binned average. So those superimposed lines and error bars are the binned deltas that we're seeing between the devices. And that is critical from a performance perspective. So highlighting those bin deltas is what you see in these charts here. So again, those bin deltas are things that is a difference that we do see between primary and cup anemometry on the left, but looking more closely at the nacelle-mounted LiDAR and that difference, particularly in the center chart that you see here, is that the bin results show that the nacelle-mounted LiDAR is giving a consistently lower wind speed versus those cup anemometers. And that is important from a power performance perspective. So when you move that wind speed into an actual power curve, for both sites, the nacelle-mounted LiDAR tends to yield a more energetic power curve. So again, when your wind speed is lower, that's going to, in essence, shift that power curve to the left. So if this was an example of a power performance campaign in the field, you would see that the nacelle-mounted LiDAR in the center chart here, that the power curve that would be yielded from a nacelle-mounted LiDAR would be more energetic compared to the primary anemometer, as well as higher than the control anemometer for both of the sites that we measured. So moving from the performance over to the other derivatives from the wind speed measurements, we want to look at the turbulence intensity. For those less familiar with the TI, it's an important input into the power curve comparison selection. So if you have a measured power curve, you're comparing that against a commercial variant. So you need the turbulence intensity to accurately select those. And it's also an important variable for an accurate performance prediction. So the four charts that you see on the right across the top, it's site 1, and you'll see it's a regression of the nacelle-mounted TI, nacelle-mounted LiDAR TI versus the primary anemometer. And the bin results, bin is a function of wind speed on the right over there. Same for site 2 on the bottom. So the main takeaways from this is that both sites are showing a high amount of scatter in terms of TI when you compare that nacelle-mounted LiDAR versus the cup anemometer. And that is the same for both sites. And the other important takeaway is that this difference that we're seeing, that higher TI, occurs across all of our wind speeds. Shear exponent, very similar to turbulence intensity. The shear exponent is important for a power curve applicability, so how we're comparing our measured versus a commercial result. It's also an important input for accurate wind characterization in a campaign. Similar to the previous charts, you have a regression for the charts on the left, as well as the bin comparison on the right for both sites, site 1 on the top, site 2 on the bottom. Similar to the TI, we're seeing significant scatter in the measured shear exponent from the lower tip to hub height. And that's important because with these tests, what is relatively standard, at least in the met mass, is to measure that shear exponent from lower tip to hub height. The regression between the nacelle-mounted LiDAR and the met mast anemometry, that regression is pretty poor. And the regression coefficients there reflect the fact that you have quite a bit of scatter and relatively poor correlation. And the bin results, although it seems a little bit better, we are still concerned with that regression that we're seeing on those left plots for both site 1 on the top and site 2 on the bottom. What we did find is that that difference is reduced. So that regression, that poor goodness of fit that we're seeing with those scattered regressions on the left there, it is improved when you start to measure the wind speed at the same elevations between the met mast and the LiDAR. And I repeat this schematic here on the left to show that we did have an opportunity at site 1 to measure that wind shear exponent at the same elevations in the met mast as we do with the nacelle-mounted LiDAR. And when we do that, that's what I'm showing in this slide here. So if we measure that shear exponent at the same elevations to the met mast as we are with the nacelle LiDAR, that reduces that scatter as well as the bin differences. And we start to see a much better goodness of fit and a much better correlation. And what this tells us, at least in the first pass here, is that the nacelle-mounted LiDAR shear exponent is not incorrect compared to the met mast. It's merely measuring the shear differently than what we're traditionally doing at the met mast, where we're measuring that shear exponent between lower tip and hub height. So to go through a couple conclusions for people's takeaway here, we did conduct 2 campaigns with this Leosphere Nacelle, excuse me, the Leosphere WindCube Nacelle-mounted LiDAR. We completed those 2 on turbines at 2 different sites in conjunction with our IEC compliant metmass. Like I had mentioned, we did not conduct the calibrations per that IEC standard. We did not execute those, but we did compare these LiDAR versus the golden standard LiDAR that comes that were conducted at the Leosphere factory, and where it was applicable, we did apply those wind speed corrections to the measured data. I mentioned the filtering criteria as we did at this first pass here. It was set up to maximize our overlap with the mass instrumentation for this kind of first principles look at the wind speed and its derivatives. And even with those smaller measurement sectors, we did have a statistically significant data set. And to recap our results, the nacelle-mounted LiDAR registered a lower bin wind speed relative to those massed anemometers in both the campaigns. And with those lower wind speeds, we had a slightly higher, more energetic power curves. And when it comes to the TI, the nacelle-mounted LiDAR yielded us a higher bin TI with high scatter versus those anemometers. And the low correlation and high scatter was also reflected in our wind shear exponent measurements. But both the scatter and the bin results improved significantly when we measured those wind speeds at the same elevations. And lastly, what's next and what we'll be looking at more closely is kind of 3 major areas. It's the impact of calibration. So if we had conducted those calibrations with this device, would those help close the gaps that we saw in those wind speed, shear, and TI measurements, and how those impact the final performance results? We're also interested in performing the evaluation with a nacelle-mounted LiDAR, considering that full IEC measurement sector, and basically treating these campaigns as a full measurement campaign per the new standard. And lastly, it's to take a closer look at that final uncertainty evaluation versus the traditional metmast. So that's the material I have for you. And with that, I will send this back over to Elvira.
All right, thank you. And well, let me reshare my screen one more time, just to basically wrap it up, the main topics that we discussed today. So it's great to see that the industry is progressing and further integrating the nacelle-mounted LiDAR measurements and power performance testing campaigns. And we are glad to get this IEC classification for our nacelle-mounted LiDAR, which is valid for current turbine sizes with different rotor diameters and hub heights. It's also good to see that WindCube nacelle measurements show great correlation with metmass measurements to perform power curve verification. We now have a few minutes to, I will stop sharing my screen, a few minutes to answer some of your questions. Let me just have a look at what we have here. There is one question to Risa on the classification. Was the sensitivity carried out on a single LiDAR unit at a single test site? Is there no requirement in the 50-3 standard for the sensitivities to be derived from multiple LiDAR units at multiple test sites?
Thank you. That was a great question. So this is a little bit different in 50-3. Really, the classification goes away. So unlike with the ground-based LiDAR or a cup anemometer, where we get a classification, a cost number, and it's done over the 3 independent units to get the unit itself. In this case, we're using a white box approach where we're taking the sensitivity that was carried out by this one study, and yes, it was one LiDAR unit, and then we're going to take the calibration of the individual unit and then the conditions at site and use that to calculate the uncertainties. So it's a little bit different in this case. So potentially calibration may not be the right word. It is actually dropped from 50-3. So in this case, we are only the requirement of doing the one unit over an extended period of time for each of the line of sight. And we've just presented here today the combined of the 4 line of sight measurements of those intermediate variables. And then on the evidence-based, as I mentioned before, we have to do 2 on nacelle tests and a minimum of 3 off nacelle tests for the evidence-based study.
All right, okay, thank you, Risa. And I think we have a few more questions on the classification. First of all, yes, here, the classification uncertainty used in performance test should take the full range or actual range in measurement.
I'm sorry.
Yeah, let me repeat it. I'm not sure if this is, maybe it's addressed to Dale. The classification uncertainty used in performance test should take the full range or actual range in measurement.
I think I can.
Yep.
Yeah, so if I can just share my slide again, just to show, maybe this will help clarify.
Go ahead.
Mm-hmm. So what we do is we look at the range of the significant environmental variable, and there'll be a significant range within that measurement, and that's outlined in the standard. So in this case, we take that range, and it depends now what range we'll use to input to get our line of sight sensitivity uncertainty. If we do not have, we'll use the calibration and the site-specific measurement to get that range. And if we don't have that, we'll just use it from the calibration of the individual unit. So here, that will use, let me take a step back. Here is that we'll take the range, those differences. If we don't have that, we'll take the range that it was observed from the classification study. And that range is defined based on the measurement range and what bins were significant and were fulfilled during this study.
All right. Okay, thank you, Risa. And I think we also have a question for Dale. So there is someone asking, is the new standard applicable to current projects? For example, would an OEM accept the results of an nacelle mounted LiDAR power performance testing where this has not been defined in the contract?
I would say right now, no. If it's a project that's the contract that's already been decided, no, I don't think that would be using the nacelle mounted LiDAR new standard. That would not apply unless it was, I would say, a special agreement that was made between the customer and commercial.
All right, okay. And there is also one more question for you, Dale, on these 2 campaigns. So someone is asking if it's possible to give a bit more insights into the characteristics of these 2 sites in terms of site complexity. I guess these are more simple sites.
Yeah, I think, as is the case with ground-based as well as nacelle-mounted LiDAR, it's a prerequisite that these sites be flat terrain as defined by the standard, by the standard. In this case, it's the 61400-1 standard, and that is the case for both of these. These are very very flat sites. And that was a critical component to selecting these as places to install these nacelle lidar.
Okay, and we do have more questions coming in. Let me have a look. Well, there is more of a general question here on where next efforts should be focused on to further encourage uptake of nacelle lidar technology, or maybe what barriers to the adoption of nacelle lidar still exist. I guess this can be question for both of us, for both of you, sorry.
Yeah, I can take a first stab at that. And kind of addresses where we were going with the next steps that I had mentioned, and this was a first pass look at the very essential parts of a performance test. And what we're seeing right away is that there are some wind speed discrepancies as well as the important variables TI and shear. And I think for us the biggest variable, or the biggest, I would say, hurdle before its widespread adoption of this is to get a good sense of, I would say, the variability in these tests and campaigns. So this being just two, where our first two installations of this, we definitely want to get a better grasp on what the calibration. So if we had conducted these tests from start to finish per the IEC standard, what those calibrations, how those calibrations would have impacted the final result, would it have taken care of the differences that we saw in those variables? And if they didn't, then as we have more tests and more experience of these devices, once we have a better understanding of the bounds of kind of variability that we're seeing, if we can understand better and be able to predict what those bounds are, that gives us a lot more confidence in, I would say, the accuracy of the final result, certainly as it compares to this industry benchmark that we've been using for so long, and that we kind of understand the limitations of it. So.
Okay, all right. And Teresa, do you have anything to add on this particular question?
Yes, I think that we see that as standards come out, such as the 2017 standard, we saw the adoption of ground-based lidars increase as OEMs became comfortable and the technology and the results were better understood. And I think we'll see the same trend with 50-3. Certainly offshore, we're doing nacelle power performance testing, and due to limitations and costs, of course, that'll be the preferred method for power performance testing. Onshore, I think that what will limit it as well is the timelines, is that you need to think about a longer timeline for that calibration of each line of sight. So that takes longer, so there needs to be some extra planning in that timeline for the calibration. And what we are seeing is we need to understand some of these measurements like TI and how they compare, but certainly we're able to calibrate the line of sight measurement for turbulence intensity, for example, and we are seeing a closer relationship to the Met mast compared to ground-based. Some initial studies are seeing. So that'll be a benefit to having being able to calibrate those intermediate variables. And so I think it's just the other side of that too is that we're just filtering in power performance testing on those. So it's not as critical as the difference as the actual wind speeds as Dale's presentation showed. So I think it's going to be up to the OEMs to get comfortable with it, for customers to get comfortable with that and understand it better. And then independent engineers such as D&V can help analyze that and help move that adoption forward.
All right. That's clear, and I think we have maybe time for one more question. So there are two questions on the independent values, environmental values from the classification. One is, which are the reference values of the independent environmental values? And there was one more that was which is the influence of the induction zone in the database, and how far must we measure to get the free wind?
So I can answer with regards to the environmental variables. I believe that was with regards to classification. So when we look at this, we look at the sensitivity. So we get a sensitivity, and we get then we compare that deviation, which is the y variable, to the x variable, the air density or wind shear, for example, and we take the slope of that and then multiply it by the range. And that range is a calculation on the binned environmental variables. And then there are some limitation of the range just from the entire range to make sure we fill those bins well and that we get a significant number in those bins. And so we get a slope and a maximum range from the study that we have done here that are then used within the project for an individual device that has been calibrated and then has a measurement on site for a power performance test. I can start to answer the second question, but I think that was directed towards Dale. So we want to measure for power performance testing this in the same distance out. So we want to be ideally between 2 and 4 rotor diameters out, and 2.5 is usually preferred within the standard, but there are some studies now looking at that induction zone and how far off we really want to be. But of course, for the lowest uncertainty, we want to be between 2 and 3 rotor diameters out. And I'll let Dale, you continue to answer that question.
Yeah, Reese, you answered it pretty well. I think if the question was how far out do we need to go to get out of the induction zone, I think the IEC standard will actually stipulate that you have to go multiple rotor diameters, even further than 4, to get out of, I would say, a flow distortion area. But yeah, at least for where we're looking for the power performance campaigns, we're still looking for that target between 2 and 3 rotor diameters upwind. As Reese had mentioned, that keeps us in the lower uncertainty area, and then like up to 4 rotor diameters maximum in terms of where we're measuring currently for these tests. And I think that's also, as it's applied to at least the nacelle mounted LiDAR in this case, is that there is a range restriction. There is a maximum range to consider with this Leosphere unit, that you can't get too far upwind. So that's also something to consider.
Okay, thank you both. And unfortunately, we are running out of time, so I suggest we stop here. And well, thank you very much to both of you and to our audience for joining us today. You can let us know if you would like to learn more, or if you want us to contact you for additional information. And thank you again for joining, and see you next time. Have a good day.